Welcome to lecture 20. The topic is p-adic integers. This is lecture 20. The topic is p-adic integers. This is often denoted as ZP. And just to recall whatever we learned from the last few lectures, so you have a prime number P, and inside Q we had this valuation ring given by the integers localized at the prime ideal P. This was a discrete valuation ring, which we call DVR. And to describe the valuation, you take an element alpha that's not 0 in Q, and you write this as a fraction. You collect the powers of P times A over B, where this A and B, they're integers with the property that they co-prime to P. Okay, and this p-adic valuation function, which we call val P, is a function from Q cross to Z, where you send alpha to this exponent n alpha. Okay, and correspondingly we had a p-adic absolute value from Q to the non-negative real numbers. And the way this was defined is, if alpha was 0, then the absolute value is just 0, and if alpha is not 0, the p-adic absolute value is not 0, and is given by the expression 1 over P raised to the p-adic valuation of alpha. And what we want to do is we want to consider the completion of Q with respect to this p-adic absolute value, and this completion is what we call QP. And the way we looked at the completion was, we had the ring of Cauchy sequences AN, and again Cauchy is with respect to the p-adic absolute value, and these are Cauchy sequences where each term is a rational number. And inside this ring we had this ideal, which was this ideal of null sequences. And again, a null sequence was just that it was a Cauchy sequence with the property that its limit was 0. And QP was defined as a quotient, and the main thing we had to show was that, well, this quotient is a ring, but the main thing we had to show is that the quotient is in fact a field. Okay, and we have natural inclusion of fields. Q inside QP, and if you take a rational number, you send it to, so remember that QP is this quotient of Cauchy sequences by null sequences. So if you have a rational number, you send it to the constant sequence alpha alpha alpha, and so on and so forth. Okay, so you send it to the equivalence class of this constant sequence. And one can extend both the p-adic absolute value and the valuation to QP and QP cross as follows. So if you take an element in QP and you lift it to a sequence, a Cauchy sequence, so any lift, say AN, of an element in QP is a null sequence or it's not a null sequence. Now, if this Cauchy sequence was in fact a null sequence, then what does it mean, its image in QP, which is just C mod n, its image equals 0. And so you just, in that case, you just define the p-adic absolute value of this null sequence to be 0. And since it's a 0 element, you don't need to define the p-adic valuation, since the p-adic valuation is only defined on non-zero elements. And otherwise, if the Cauchy sequence an is not a null sequence, then we applied this lemma 43 from one of the earlier lectures, and what that told us was that there exists a natural number which we call n naught, says that for any index little n that's bigger than this n naught, we have that those numbers are the p-adic absolute value of an equals the p-adic absolute value of an naught, and that's not 0. Okay, and so in this case, when the Cauchy sequence is not a null sequence, you define sorry, the p should be outside. You define the p-adic absolute value to be the p-adic absolute value of this an naught. Okay, so if you want, you can also put a bar to denote that an element of QP is an equivalence class of these Cauchy sequences. And for a sequence that's not a null sequence, the p-adic absolute value, the p-adic valuation is defined to be the p-adic valuation of an naught. Okay, and I leave this as an exercise to you to show that the definition of the p-adic absolute value and the p-adic valuation does not depend on the choice of lift an to C. Okay, and that in fact this function from QP cross to Z defines a valuation on QP cross. Okay, so in fact you get a p-adic valuation or a valuation on QP cross that takes value in Z. So in particular, the value group is still Z, and ZP is defined to be the valuation ring for this valuation val P on QP cross. Okay, so in particular, it's the set of all elements in QP cross such that the valuation is larger than or equal to the 0 element along with the additive identity of QP. Okay, and its maximal ideal, let's call it MZP, is the set of all elements in QP cross such that, well, the valuation is strictly larger than the additive identity. Okay, but your value group is Z, the integers. If you're strictly larger than 0, then you must be at least 1. So the maximal ideal is in fact the set of all elements in QP cross such that the p-adic valuation is larger than or equal to 1 along with the additive identity. Okay, and so here's the next lemma. So we know that ZP, because its value group is Z, it's a DVR, which means it's a PID, which means that the maximal ideal must be principal. So let's try to find a principal generator for this maximal ideal. So that's the next lemma, that this maximal ideal is in fact generated by P. Okay. And what do I mean by P? So the element P of the integers sits inside ZP. And how does it sit inside ZP? By this constant sequence P, 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 and so on. Okay. So by this element, I mean the equivalence class of the constant sequence P, 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 and so on. And it's not hard to show, so it's not hard to show that, if you look at the p-adic valuation of this constant sequence, well, every element is P. So if you take the p-adic valuation of any element, it's just a valuation of P, and you get 1. Okay. Okay. So in particular, so this element P belongs to the maximal ideal since its valuation is strictly positive. So remember that the valuation is 1, which is strictly positive. So P belongs to MZP. So in particular, the ideal generated by P belongs to the maximal ideal. So in fact, PZP sits inside the maximal ideal. Okay, and in fact, for any exponent R which is larger than or equal to 1, you can play the same game. We can view P to the R of the integers inside ZP via the equivalence class of the constant sequence P to the R, P to the R, and so on and so forth. So again, we have this inclusion Z into ZP, and P to the R just maps to the equivalence class of the constant sequence P to the R. And again, the valuation of this constant sequence, you can take every element is P to the R, so you can take the valuation of any element, and that's just R. Okay, so now consider an arbitrary element in MZP, and consider a lift, let's say AN in C. And what we want to show is the reverse inclusion. We have already shown. So we've already shown that PZP sits inside the maximal ideal. We want to show that these two ideals are the same, so we want to prove the reverse inclusion. So we want to show that the maximal ideal sits inside PZP. And so assume, without loss of generality, that this lift AN is not a null sequence. If it was a null sequence, it maps to the 0 element, and the 0 element belongs to all ideals. So without loss of generality, we'll assume that this lift is not a null sequence. And again, by applying lemma 43, there exists an n naught says that the absolute value of the p-adic absolute value of an and the p-adic value of an naught, they match up, they're equal. But what's the p-adic value, absolute value of an? It's 1 over p, the p-adic valuation of an. This equals 1 over p, the p-adic valuation of an naught. And so in other words, and this is true for all little n larger than n naught. So in other words, the p-adic valuation of an matches the p-adic valuation of an naught for all n larger than n naught. Okay. And since by assumption this sequence lives an element in M, the maximal ideal, well, these p-adic valuations must be strictly larger than 0. So we must have that the p-adic valuation of this sequence or its equivalence class, which by definition equals the p-adic valuation of this an naught, must be strictly 0 or larger than or equal to 1. Okay. So let's call this number, say r, call this positive integer r. And now consider a new sequence Bn with the property that Bn is an over p to the r. And now since the sequence an is Cauchy, and since Bn is just formed from an by scaling by this factor 1 over p to the r, we have that the sequence Bn is also Cauchy. And if you consider the p-adic valuation of an, this is nothing but the p-adic valuation of an over p to the r plus the p-adic valuation of p to the r. So I'm just using the fact that an can be written as an over p to the r times p to the r, and I'm using the fact that the p-adic valuation is multiplicative. But what's an over p to the r? That's just Bn. So now we have that the p-adic valuation of an equals the p-adic valuation of Bn plus the p-adic valuation of p to the r. But if little n is larger than n naught, then we've just seen that the p-adic valuation of an equals r. And so what this means is that if little n is larger than n naught, then the p-adic valuation of Bn is in fact 0. Okay. So in other words, the sequence, this Cauchy sequence Bn, so has the property that its p-adic valuation well, it's not a null sequence because the sequence an was not a null sequence. So if you scale it by p to the r, you still can't go to 0. So the sequence Bn is not a null sequence. And what is its p-adic valuation? Again, we see that eventually all the p-adic valuations are just given by this one quantity, it's 0. So eventually all these p-adic valuations, they match up and they become 0. So in particular, the sequence or the equivalence class, the equivalence class of the sequence belongs to Zp since its p-adic valuation is equal to 0. Okay, and now observe that an is nothing but bn times p to the r, which implies that the sequence an equals the sequence bn times the constant sequence p to the r. So this is just a constant sequence p to the r. Okay, so in particular, so this is an equality in C, and so if you take the equivalence class, you get a similar equality. Now what we have is that the equivalence class of Bn belongs to Zp. So the first term here belongs to Zp. The last term here is nothing but p to the r. So what we have is that the equivalence class of the sequence An in fact belongs to pZp, since it belongs to p to the r Zp with r being larger than or equal to 1. And so in other words, what we've shown is that this arbitrary element, which is not a null sequence in the maximal ideal, belongs to pZp. So this gives the reverse inclusion, and so we've shown that the maximal ideal is in fact generated by P. So it's this principal ideal generated by this constant sequence P. So we've shown what we wanted to prove. Okay. So some more facts from topology. So we've defined QP as the quotient of Cauchy sequences, where each element in this Cauchy sequence belongs to Q. And we can ask a question whether the field that we get is complete with respect to the p-adic absolute value. Again, it's one of the standard arguments from topology. It's called the diagonalization argument. You can use the diagonalization argument to show that QP is in fact complete. So I'll only sketch this argument. So to show that QP is complete, you want to take an arbitrary Cauchy sequence, let's call it Xn. You take an arbitrary Cauchy sequence in QP, and the question is, does this Cauchy sequence have a limit in QP? And so one of the obstacles is that you're taking Cauchy sequences of Cauchy sequences. So for example, if you look at the first element of this Cauchy sequence, that itself is a Cauchy sequence. Where each element of this Cauchy sequence, let's call it an1, belongs to Q. And now similarly, if you look at the second element of this Cauchy sequence of QP, that element itself is another Cauchy sequence. So you have a12, a22, an2, and so on and so forth, again with each term an2 belonging to Q, and so on and so forth. If you look at the arbitrary, let's say the mth term, you have a1m, a2m, and so on and so forth, with each a&m belonging to Q. Okay, and again, to show that QP is complete, we need to construct a candidate for this limit as m goes to infinity of this Cauchy sequence xm, and so this candidate has to be a Cauchy sequence itself. Where the elements are in Q, and so The way you do that is you use some sort of diagonalization argument. So you take the first element of the first Cauchy sequence, the second element of the second Cauchy sequence, and so on and so forth. So you take y to be a1, 1, a2, 2, so on and so forth, a and n. And so what you have to show is that y is a Cauchy sequence in Q, again Cauchy with respect to the p-adic absolute value, and in fact show that the limit as m goes to infinity of this x to the m equals y, or maybe in its equivalence class in QP. Okay, this is sort of standard argument, so I'm leaving this also as an exercise to the student. But the reason I brought this up is you can look at a subring of C, which is the ring of Cauchy sequences an, with the property that each term is in fact in Z. Okay, so instead of looking at all Cauchy sequences where these elements are in Q, now I restrict myself to Cauchy sequences where each element is in Z, and I look at null sequences inside that. So it's I look at nz to be the ideal of null sequences an, where again each element is in Z. And again by null sequence I mean that if you take the limit as n goes to infinity of an, it equals 0. And I define Z1 to be this quotient as earlier, Cz mod nz. Okay, now similarly you can play the same game. Instead of looking at Z, now you can look at, say, Z localized at P, that's a DVR. So you look at the ring of Cauchy sequences an, where each an belongs to this DVR, this Z localized at P. And again, when I say Cauchy, I always mean with respect to the p-adic metric, p-adic absolute value. And again, you can look at the null sequences inside CZP. So I look at the ideal of null sequences an with the property that each term is in Z localized at P, and the limit as n goes to infinity of an equals 0. Okay, and again by a similar diagonalization argument, one can show that Z1, and let me call Z2 as the quotient of Z of Cz localized at P modulo the null sequences for this discrete valuation ring. So these are complete with respect to the p-adic absolute value. Okay, and again since Z sits inside Z localized at P, it sits inside Q, we have natural inclusions Cz mod nz sits naturally inside C Z localized at P modulo the null sequences for this DVR sits inside C mod n. In other words, we have that naturally we have Z1 sits inside Z2 sits inside QP. Okay, but note, observe, if you have an element alpha in Z localized at P, then you write alpha as p to the n alpha times a over b. Then the p-adic valuation of this alpha, which is n alpha, is larger than or equal to 0. So if you take so in fact, if you have a sequence So if you have a Cauchy sequence, say an in C Z localized at P, then since each element is in Z localized at P, the p-adic valuation of any equivalence class is in fact greater than or equal to 0. Okay, so in fact, if you look at Z1 sitting inside Z2 sitting inside QP, you see that every element of Z2 must actually have p-adic valuation larger than or equal to 0. So in fact, Z1 sits inside Z2 sits inside ZP. Okay, because the previous observation tells us that the sequence, since its valuation is larger than or equal to 0, it in fact belongs to ZP. Okay. Okay. So what we want to show next is this proposition. So we call it proposition 49, that in fact Z1 equals Z2 equals ZP. So we have the proposition 49. What we want to show is that Z1 equals Z2 equals ZP, and we'll complete the proof of the proposition in the next lecture. Thank you.